All right, we are going to review the techniques of integration.
Wait.
In fact, this year, I think we might discuss the z substitution.
Is that
It was in the calculus book last year, but you guys probably forget. No, all of this hinges on whether you guys. I'm assuming everybody knows what's on the list to even begin with. So the simplest technique so after we memorize the list.
Can you put the list on there?
No, you guys have it on it's on the website.
So the list being like all the.
Yes.
The list of integrals. Do you guys have the same list? Mr. EA?
Yeah.
Okay. So the first technique we need to discuss is U substitution. Okay, shall I give you a simple example? Shall we do a simple one?
Yes, please.
Okay, how about natural log x over x dx?
U equals natural log x.
Okay, there you go. So the first thing you ask yourself is when you see an integral, is it on the list? If it's on the list, you just write the answer down, right? If it's not on the list, then we got to use these techniques. So the first thing, you always try the simplest thing first, U substitution. Can I make a substitution to transform this integral into an integral that I know? And the answer is yes. We do a U substitution. U equals chosen natural log x. Why?
Because there's an x out of the block.
Yeah, because du is 1 over x dx.
Oh, I remember this.
And how do you know if a U substitution is going to work? Well, with whatever you let u equal to, du also has to be in the integral so you can substitute for it, right? Yes. So this integral becomes, what is that? U. And what is dx over x? Du. And then now can I do that? Yeah, it's on the list. 1/2 u squared plus c. And then resubstituting back in, you get 1/2 natural log x quantity squared plus c. So that would be your typical U substitution problem. Okay, let's do another one with limits on it. Integral, okay, let me think. Square root of 1 plus cosine x. Wait. 7 cube root sine x dx from 0 to pi over 2. There, I just made a problem. Okay, now does that look like it's on the list?
No.
No. Can I make a substitution so that the transformed integral will be on the list?
Oh, yeah.
Yes, so what should I let u equal to?
1 plus 7.
1 plus 7 cosine x. Now, some people, they let u equal cosine x, that would work. 7 cosine x, or even 1 plus 7 cosine x. But if you let u equal to the entire thing in the radical, that's probably the best thing to do. Therefore, what is du? What is the derivative of 1 plus 7 cosine x? Park.
Negative 7 sine x.
No. dx. Because remember, it's actually du over dx. We're multiplying the dx on that side.
Yeah.
Now, is this substitution going to work?
Yes.
Yes, because sine x dx is in the integral as well, so we can substitute for it.
Negative.
So this integral becomes cube root of u on the bottom, and what do I substitute for the sine x dx right there? Right there.
du.
du over negative 7, so we throw the constant on the outside. And then, when you make a u substitution, the limits change. What are the new limits going to be? How do you figure out what the new limits are going to
Plug
be?
in.
You plug in these limits into the substitution you made here. So if I plug in 0 for x there, what do you get? 8. And then if I plug in pi over 2 for x there, you get 1. This integral is on the list. So you get negative 1/7, and what is the integral of 1 over the cube root of u? Huh? What is the antiderivative? Because to compute an integral, you got to compute the antiderivative.
4u to the 4/3.
Okay, this is the same thing as u to the negative 1/3, right?
Oh, u to the 2/3 over 3.
Times 3x. From 8 to 1, factor out the constants, so you get negative 3 over 14, plug in the top number. This is the fundamental theorem of calculus part 2 here. Plug in the top number, 1, minus plug in the bottom number,
4.
4, and so you got 9/14. Boom, there's your answer. So when you make a u substitution, you gotta change the limit. Now, there are some problems where it looks like you can't do a u substitution, but you can. Let me show you one. How about the integral of x over square root of x plus 1 dx? Now, that's not on the list, and it doesn't look like you can make a u substitution, but you can. What would I let u equal to?
Square root of x plus 1.
No. Oh, shoot. I guess you could. You could, but I think it's easier if you just let u equal x plus 1. Why? Because then what is du?
1.
Dx. So, what do I substitute for that there? Radical u. What do I substitute for the dx? Du. Yo, Mr. Park, what do I do with this x? Well, what can I substitute for the x? Look at this. What can I substitute for x? U minus 1. Can I do that integral? How do I do that integral? Come on, these are all the techniques we learned last year. What do you do when you have a single term in the denominator? Lift and separate. Did you guys learn lift and separate? Like split it up into separate terms.
Probably, but not
So what is u over root u?
Root
U to the half minus what is 1 over root u? U to the negative half. Can or cannot? The answer is can. So u to the 3 halves with a 2/3 in the front minus u to the 1/2 with a 2 in the front plus c. Can I leave my answer like that?
Yeah.
Yeah, you can, but you're going to get minus 1 or 2. Because if the original problem is in terms of x, your answer should be in terms of x. So now you need to resubstitute back in. What was u equal to? Resubstitute back in, so your final answer is going to be 2/3 x plus 1 to the 3 halves minus 2 x plus 1 to the 1/2 plus c. Now, lots of these problems can be done in more than one way. Like Cho said, let u equal to root x plus 1. I think that would work as well. In fact, let's just try for funsies.
Wait.
Well, let's just try. What if you let u equal root x plus 1? Then what is du equal to? 1 over 2 root x plus 1 dx, right?
That doesn't work.
Well, let's just try.
Yeah.
So, what is dx over root x plus 1 right there? What is dx over root x plus 1? Here, circle it. 2 du, correct? Move the 2 on this side.
Yeah.
This is simple algebra, people.
Yeah.
But then, what do I substitute for the x there? Well, according to this, what is x equal to? Well, if you square both sides, you get u squared equals x plus 1. So what is x equal to?
U squared minus
U squared minus 1. So that's going to equal 2, 1/3 u cubed minus u plus c. And if you resubstitute back in the u, you get the same answer. Yes, you could have done it that way.
Oh,
That also works.
nice.
That also works. So yeah, sometimes there's many different ways of doing the problem. In fact, I just thought of another one. How about this? Integral sine x cosine x dx. There's many ways of doing this problem. Give me one, Cho.
That's equal to 1/2 sine 2x.
Okay, so one is to use a trig identity. So isn't this equal to 1/2 sine 2x dx? Can I assume we remembered our double angle identity? Can I assume that we know that sine 2x is equal to 2 sine x cosine x?
Yeah.
Okay, so isn't that this? And then, hey, that's on the list. So what's the answer? Wayne, this is on the list. Negative. Come on, sine
Oh, it's-
sine u is on the list. Okay, I'll give you a hint. The integral of sine u is negative cosine u plus c. So that's my negative.
Negative cosine 2x
Plus C. But then, how come I left a space there?
Wait.
So what is this thing that's here?
1/4.
Yeah, 1/4. How come 1/4? Because the derivative of the box is 2. You have to adjust for the derivative of the box, put a 1/2. So 1/2 times 1/2 is 1/4. Okay, that's one way to do the problem. But some other people might say, hey, can't I do a u substitution here? Can't I go u equals sine x? Does that work? Yeah, and then what is du? Cosine x dx. So this integral becomes u du, right? Which is 1/2 u squared plus c. Resubstitute back in, you get 1/2 sine squared x plus c. Yeah, what is the part? There's a different answer. Or is it? Well, shouldn't the answers be the same? Since it's the same problem. Yes, the answers are, in fact, they are the same. So now you tell me, why is this the same thing as that?
Consider plus c.
Because what cosine 2x, what's an identity for cosine 2x?
Oh,
1 minus 2 sine squared x. What happens when I discretize this negative 1/4? You get negative 1/4 plus 1/2 sine squared x plus c. Why is this answer the same thing as that? Because negative 1/4 is a constant. A constant plus a constant is simply a constant. So they are the same answer.
Amazing.
No, this is not amazing. Yeah, but Mr. Park, couldn't you have done this then? U equal cosine x, du equal negative sine x dx. So this integral becomes u negative du, which is negative 1/2 u squared plus c. Resubstitute back in negative 1/2 cosine squared x plus c. Yeah, you could have done it that way also. Why is this answer the same thing as this? Again, by trig identities. Instead, okay, cosine 2x, remember there's 3 identities?
Yeah.
This is one of them. What's the other one?
2 cosine squared x minus 1.
Look how many Joe, where's the... Come on, do I need to give you guys the trig identities? Do I have to post it? Okay, I will.
Hey, Mr. Park.
Okay, wait. So if I distribute this negative 1/4, you're gonna get negative 1/2 cosine squared x plus 1/4 plus c. Why is that the same thing as that? Because a constant plus a constant is a constant. Okay, so what's the question?
Why is u equals sine x not sine 2x? Oh wait, never mind.
No, see this one we used the trig identity. This one with both these we did u substitution.
Oh, okay.
But see, no matter what technique you use, you should get the same answer, right? No matter what. And they are, even though they look different, they are the same. Okay, so that's u substitution. What's the next technique we learned last year? What happens if you can't do a u substitution? Okay, let me give you an example. What if you get the integral of x squared ln x dx?
Oh, it's.
It's not on the list. You cannot make a u substitution. So what do we use? Integration by parts. Now, you guys remember the formula for integration by parts?
uv
The integral of u dv is equal to
uv
uv
minus
minus
integral
v du. There, integration by parts. So this is a perfect candidate for integration by parts. So you go u du dv and v. Now, if you forgot how integration by parts works, one of the parts you're going to let equal to u, the other one is dv. So you have to decide which one is which. So what should I do?
ln x.
Should I make u at the x squared, or should I make it the natural log x?
Natural log.
Why?
You can't take the integral.
Yeah, because natural log x, the derivative is 1 over x dx. dv, if that's the x squared dx, then that would be 1/3 x cubed, right? What if you switched it? Then this one would be x squared, easy to take the derivative, but natural log x, do we know the antiderivative of it? Actually, we do, but that's okay. Let's just pretend we don't. Here, let's just do this problem. So, applying the integration by parts formula, the integral of u dv, which is the thing we're trying to find, is equal to uv minus the integral of v du. So that's 1/3 x squared dx. So, in order to do this integral, you gotta be able to do that integral. Can do?
Oh,
Yeah, that's easy. The integral of x squared, my dog can do that. 1/3 x cubed, natural log x minus, what's this one? That's 1/3 x cubed, right? So 1/9 x cubed, and please don't forget to put the plus c. Boom, integration by parts. So, there's a certain order you want to do integrals, like I said. Is it on the list? Next thing, u substitution. If you cannot do u substitution, then the next thing is integration by parts. Okay, we gotta look at some more examples. Okay, how about something like this? Integral of e to the root x dx. Or do you rather do cosine or sine? Let's do e. That's not on the list. Can I do a u substitution?
oh, wait.
It doesn't look like you can do a u substitution. See, this would be a harder problem. But let's try. If you were to make a u substitution, what would you let u equal
Root
to?
x.
Yeah, root x. Then du would be what?
2.
1/2 root x dx, right?
Yeah.
Okay. Now, it doesn't look like you can do it, but let's just try. What do I substitute for that? E to the u. What do I substitute for dx?
2 root x.
2 root x du. Now, if you're going to make a u substitution, we need to have everything in terms of u, but that's not u, or is it? What can I substitute for root x right there?
Oh, u.
U, it is u. That's u. So this whole integral becomes 2u e to the u du. Now, that's a perfect candidate for integration by parts, but remember last year we learned a shortcut?
Tabular.
Tabular integration. Now, like in this one, you cannot do tabular. Why can't they use tabular in this? In order to use tabular integration, one of the parts got to be able to differentiate down to 0, which this one can. But the other part, you have to be able to repeatedly integrate. You know what I'm talking about?
Oh, yeah.
So you can't repeatedly integrate that. You can't even do it once. So that's why this one you just have to do regular integration by parts. However, something like this can be differentiated down to 0, right? What's the derivative of 2u? 2. What's the derivative of that? 0. So you can take it down to 0. And then the other one, you can repeatedly integrate. What's the integral of e to the u? E to the u, e to the u, and then remember this? Hanka, plus or minus. Always start with plus and it alternates, yeah? So the answer is going to be this times positive 1. So 2u e to the u. This times -1. Minus 2 e to the u. Put plus c. And then your last step is just to resubstitute back in. So the answer is going to be 2 root x e to the root x minus 2 e to the root x plus c. So this problem here incorporated 2. We did a u substitution first, and then integration by parts. Oh my goodness. Okay, and then
Oh!
Isn't it on the video?
we're past this problem.
I'm sorry, I'm slow.
How about
right
watch the video? How about take a picture?
No.
Why not?
No storage space.
Are you serious?
How about watch the video then? If you watch the video, can you take a snapshot?
No. Because no storage.
Oh, yeah.
What?
What have you been doing? I don't want to even know, right? Oh my.
Yeah.
Downloading videos? What kind of videos?
Corn videos.
Okay, now what about something like this? Integral, let's see if you guys can remember how to do this. E to the x cosine 3x. Let's put 2 and 3 then.
about the parts?
Yeah, you do integration by parts, except there's a twist to it.
Oh, you gotta do it again.
Yeah, you gotta do it twice.
Yeah.
This is called solving for the unknown integral. Okay, so you do regular integration by parts, so dv. So which one do you want to let u equal to u, the exponential or the trig function? It doesn't matter as long as you do it consistently.
The trig.
What?
The
Okay, let's do the exponential. And then this one is the trig function here. It doesn't matter as long as you do it consistently on the first and the second one. So fill in the chart. What goes over here? Wang.
2e to the 2x.
Dx.
Oh, yes.
And then what goes over here, huh?
1/3 sine 3x.
Dx.
No.
Well, actually plus c, but we're not going to put the plus c until later. So, following the integration parts formula, the integral of u dv, which is the thing we're trying to find, is equal to uv, 1/3 e to the 2x sine 3x, minus the integral of v du, which is 2/3 e to the 2x sine 3x dx. So in order to do this integral, you got to be able to do this integral here. But that integral looks very familiar, very similar to the original problem. So what do?
When
You do it again. So u equal du equal dv and v. So this is where you keep it consistent. If you let u equal to the exponential function in the first one, you gotta let it equal to the exponential function in the second one. Otherwise, you know what's gonna happen? You're gonna end up with 0 equals 0, which is true, but it's not gonna help you. So I'm just gonna fill this in quickly. Negative 1/3 cosine 3x. Did I do that correctly? The answer is yes, I'm the teacher. So, the box, remember we did the box and the oval last year? Does that sound familiar? Cho wasn't even listening. So this box over here, the box is equal to uv, negative 1/3 e to the 2x cosine 3x, minus the integral of v du. So what's that going to be? Plus 2/3 e to the 2x cosine 3x dx. So let's put it all together now. So you see this original integral that we're trying to find? Let's call that oval so we don't have to write it out. Oval is equal to 1/3 e to the 2x sine 3x minus 2/3 of the box. But this is the box. So you have to take this negative 2/3 and distribute it here. So what are you going to get? Take negative 2/3 and distribute it. Plus, okay, I'll do it. 2/9 e to the, I know how to do this. You guys got to be able to do it. 3x minus 4/9 that. But isn't that the problem that we're trying to find? That's oval. Does this look familiar? Huh?
Yes.
Okay, so what do you do then? We solve for the unknown integral. You take this oval and bring it on this side. So if I add 4/9 oval to both sides, what are you going to get?
13.
This is 13/9 oval. I'm going to erase this. And then how do you solve for the oval? Multiply both sides by 9/13. So oval is equal to 9/13, 1/13 e to the 2x sine 3x plus 2/9 e to the 2x cosine 3x. And please don't forget to put the plus c. Woo! That's solving for the unknown integral. Now, tonight's homework, we're going to spend 2 nights on it. Believe me, it includes all the techniques. Okay, so these are the techniques we learned, but then there's more. There's 2 more techniques we got to cover. I'm erasing this. The left.
Yeah.
Okay, what is the next thing on the list? Should we do partial fractions or trig substitution? Which one you want to do first?
Trig?
Trig substitution, okay. Trig substitution. If you see these expressions in an integral, x squared plus a squared, x squared minus a squared minus x squared, and you cannot do any of the other ones, then that's when you use trig substitution. So, what substitutions do I do for each other? Do you guys even remember? This
Tangent
one,
plus.
you would let x equal
Tangent.
a tangent,
Oh, a tangent.
a tangent theta. This one, you would let x equal
Sine.
a
Sine.
secant theta.
Ah.
And this one, you would let x equal
A sine.
a sine theta. Now, why do you do that? Because when you make the substitution, you get a trig identity, Pythagorean identities. Okay, let's look at one example. Okay, you guys are going to ultimately have to do this on your own. Which, okay, let me think. How about integral? No, you guys got to do that one for homework.
What?
I know, I'm trying to think of problems that like, because you guys gotta do it on your own, man.
Oh, really?
Square root 1, now let's do 4 minus, no, what am I doing? Yeah, 4 minus x squared dx. Okay, let's do that. No, that's too easy. That's too easy. Right? Okay. No, let's do it, let's do it. 4 minus x squared dx. Okay, it's not on the list. Cannot make new substitution, integration by parts, no. So, trig substitution. So what would my substitution be? X equals
2 sine.
2 sine theta. Dx then will be
Oh.
2 cosine.
2 cosine theta d theta. What? No, no, we're doing derivatives here. So this integral becomes 4 minus x squared. Now if this is x, what is x squared?
4 sine.
4 sine squared theta. And dx is all of this, 2 cosine theta d theta. So this becomes 4, factor out the 4, 1 minus sine squared theta. Now do you see why that substitution works? Because 1 minus sine squared theta is cosine squared theta. It's an identity. So 4 cosine squared theta. So if I take the square root of that, what are you going to get? What's the square root of 4?
2
2. What's the square root of cosine squared theta?
cosine.
No, absolute value of cosine theta. However, if I do give you a problem like this, I probably would put a restriction. I would probably say that x is between 0 and 2, so that you don't have to worry about the absolute value. You know what I'm talking about?
Yes.
But it's actually absolute value there. 2 cosine theta d theta. So what does this become? 4 integral of cosine squared theta d theta. And we know how to do that. That's on the list. Right, Park?
Yeah.
What is it? What is the only way in the whole world to integrate cosine squared?
1/2 minus.
Hey, very good.
Minus cosine
You have to replace it with the identity 1/2
plus.
plus
Cosine.
1/2.
1/2 cosine 2 theta.
That was very good. Yeah, you guys remembering stuff. Wayne, you remember that one? So, that's going to be 4 times 1/2 theta plus 1/4 sine 2 theta plus c, and let's go up here. Woo! So what happens when I distributize that 4? You get 2 theta plus 1 sine 2 theta plus c. Box that, that's the answer.
Oh,
No! If the original problem is in terms of x, the final answer got to be in terms of x. So do you guys remember how to change it back into x's?
oh my. Don't you like sine inverse it?
Yeah, so here, you look at this, your original substitution. Isn't that saying the same thing as sine theta equal x over 2? If you move the 2 on this side. So then you draw a triangle. Sine of theta, what is sine? Opposite over hypotenuse, and then you Pythagorize 4 minus x squared to get the third side. Now you can change it. So 2 times theta, what is theta? Look at any one of these. What is theta? Here, look at this one. How do I move the sign on this side? Divide both sides by side. How do I get rid of the sign? You sine inverse it. So theta is sine inverse x over 2 plus, now what is sine 2 theta? There's an identity for that. What is the identity for sine 2 theta?
2.
2 sine theta cosine theta plus c. So what can I substitute for sine theta and cosine theta? You look at the triangle. What is sine theta?
Oh.
Opposite over hypotenuse. So x over 2. And then what do I substitute for cosine theta?
Square root.
Adjacent over hypotenuse. 4 minus x squared over 2. So your final answer going to be 2 sine inverse x over 2 plus these cancel out 1/2 x root 4 minus x squared plus c. There you go, that's your answer. Wow! Forgot a lot then, huh? That's why we're reviewing. Okay, and finally, the last technique we're going to discuss today is integration by parts. No, not parts, partial fractions. Partial fractions. You remember partial fractions, Wayne? A little bit.
Yeah. Is that like where you use the heavy side thing?
Yeah, heavy side, or sometimes you can't use heavy side though, yeah?
Yeah.
I mean, you can always use heavy side. Okay, let's just do a simple one. Integral, how about dx over x squared, no! X times x squared plus 1. Okay, no, I'm just debating what we're, you know what? I think we should do x squared times x squared plus 1. Okay, actually this problem you could do two ways. You could do, a trig substitution would work on this as well. You know why?
The x squared.
Yeah, because you got this expression right there. So you could actually do a trig substitution. You could let x equal 1 tangent theta. But if you had a choice, remember we talked about this last year. If you had a choice between trig substitution and partial fractions, which one would you rather do? Partial fractions is usually simpler. Okay, so let's do it. So in order to, so what we gotta do is we gotta decompose this into its partial fractions, okay? So you guys remember how?
Yeah.
What fractions do I have to add together so that this will be the least common denominator?
X.
A.
A over x plus b over x squared plus something over x squared plus 1. What goes up there?
C.
Cx plus d.
Yeah.
How come there's a cx plus d over there?
Because
Because it's an unfactorable quadratic. So whatever the degree is, if it's x squared plus 1, you got to put it 1 degree smaller. See, 1 degree first and 0 degree. What if you had an unfactorable cubic like this? X cubed plus 2. I'm not going to give you this, but what if you did? What would go on top?
CX.
Ax squared plus bx plus c. It's always got to be 1 degree and 1 or smaller. Or, yeah. Now, what about this thing? How come x squared, we had to go a over x plus b over x squared? You guys remember that? We call that a repeated linear factor. So, this is a linear factor, but it got repeated with the square there. So that's why you have to have the square and the one before. So here, let me try to clear this up better. What if this was x cubed instead? What if it were an x cubed there? How would you decompose it? You would go a over x plus b over x squared plus c over x cubed. That's called a repeated linear factor. Now, so the whole key with doing partial fractions is you got to be able to decompose it correctly, because if you don't, we call that a fatal error. Okay, now what? Come on, we're seeing the light at the end of the tunnel now. Okay, multiply both sides by the LCD, so you're going to get 1 equals ax, x squared plus 1, plus b, x squared plus 1, plus cx plus d times x squared. Now you have to decide, do I want to use Heaviside method, equating the coefficients, or a hybrid of the two? You guys remember that hybrid? Art? Eyes glazing over already?
No, so something that
Don't worry, we'll watch the video later.
I won't.
Wow.
So come on, tell me, what do you guys want to do? Heaviside the thing? equate the coefficients or hybrid?
Hybrid.
Coefficient.
You guys even know what a hybrid means?
Yeah, yeah.
I don't know.
Okay, in order to do equating the coefficients, which is part of the hybrid method, is you gotta multiply out everything.
Oh, that
So
means
you,
I do that.
too late, I'm doing it. Ax cubed plus ax plus bx squared. Don't worry, you don't have to worry. It's gonna be a long, hard work, no matter what you do. Okay? Plus cx cubed plus dx squared. So this is equal to, okay, combine all the x cubed terms right there. Here's x cubed. What's the coefficient gonna be? A plus c. Then you combine all the x squared terms together, which is this and that. What's the coefficient? B plus d. Then you combine all the x terms together. Where's the x term? Only got a there. And then the last thing is the constant, which is b. So equating the coefficients means that the coefficient of x cubed on the right gotta equal to the coefficient of x cubed on the left. Therefore, a plus c gotta equal 0. And then b plus d gotta equal 0 because there's no x squared term on this side. A gotta equal, wait, this is junk then.
Oh, it's all 0.
Then C is 0.
This is junk.
Here.
This is, something is wrong here. This is junk. A is 0. That means C is 0. Oh, that's okay. It's just going to make it easier. Okay, you know what? I should have put something else on the top, like 2x plus 1. But I didn't. Don't worry, the one on the test not going to be this easy. So A is 0 and B got to equal, what does B have to equal? 1. The constant got to equal to the constant. So according to this, we don't even have to do a hybrid. It's right in front of our face. If A is 0, doesn't that mean C got to be 0?
Yeah.
And if B is 1, D got to be negative 1. So if I, oh, this is junk. So anyway, the technique is the important thing. So this becomes, this is 0, B is 1, so 1 over x squared, and then C is 0, so you just got D is negative 1 over x squared plus 1. There you go. So this integral is equal to the integral of 1 over x squared minus 1 over x squared plus 1. That's junk! So what's the final answer then? Let's write the answer down here. Come on, these are both on the list.
Oh.
Negative 1 over x
Minus 10 inverse.
minus 10 inverse x plus c. Ah, that's too simple for you guys. That's way too simple for you guys. Don't worry, I'll challenge you on the test. So those are all the techniques. Now there is one other technique that we didn't cover. It's called the z substitution.
What would you do something like that?
No, maybe we'll do it. Do I see you tomorrow?
No.
No, Thursday. Maybe Thursday we'll cover it. It's in the book.
We didn't do that last year.
No, we didn't. Okay, but these are the basic techniques, and the z substitution is like a bonus thing. But believe me, in this course, these are going to come up all the time. So that's why we have to do. You have to be good at integrals, otherwise you're in trouble. Because think about it. What did we use integrals for last year? Finding areas, right? Surface areas and volumes. So what do you think we're going to do in 3 dimensions? We're going to find surface areas and volumes. And then we can extend it to even 4 dimensions if we want. Do a 4-pole integral. Because later we're going to do double and triple integrals, and if we want, we can do 4-pole integrals.
Is that even possible?
You know?
Oh.
All right. What time does this class end?
In 20.
45. Yeah, so we've got 25 minutes left. Maybe you guys should start working on the integrals there. Okay, I got to start uploading this video. So you got 2 days to do this. So at least try the first 7, and you have questions. We'll go over it on Thursday. Yeah? So in this class, there are no quizzes now. It's only going to be a test. You're going to hand in your homework. You know what? I'm going to give you 10 points for each homework assignment, and then you take the test.
And your test is